What's more, we as people are not sadly savvy to the point of grasping them. Andromeda, our cosmic neighbor, can be seen in our skies without a telescope, which is fascinating. However, things have gone from intriguing to upsetting and disturbing. Michio Kaku has uncovered that the James Webb Space Telescope has received troubling signals coming from Andromeda, and these signals end up being significantly more perilous than ever expected. Join us on this journey to discover the truth behind these disturbing signs and how the future could undeniably be more frightening than we ever imagined. Andromeda is an infinite giant with intriguing qualities that distinguish it in the vast universe, otherwise known as M31 or more chaotically 31. It is the largest cosmic system in our region, with a noteworthy diameter of roughly 220,000 light-years, a genuine heavenly miracle in regard to its infinite size. Albeit the Andromeda world lies at a significant distance from Earth, around 2.5 million light-years away, its position in the universe places it beyond the limits of our cosmic area. Despite the fact that its size might be startling, it is also captivating to notice its structure. Andromeda shares a comparable foundational layout to our own Milky Way system, with a barred spiral design. This element is featured by a central lump of matter encompassing a flat plate containing stars, gas, and vast dust. Its even structure shows the amazing complexity of this universe. As far as its heavenly population, Andromeda is home to an astounding 1 trillion stars, far surpassing the number of stars in our own Milky Way, which has around 250 billion stars. This explains why it is so noticeable from Earth, since its brilliance is surely a more prominent indicator. However, loftiness and glow are not the only fascinating attributes it has. Open space conceals numerous secrets, and every system has unique and astonishing characteristics. At the center of the Andromeda cosmic system, a concentrated lump of matter stands out in the spiral design of the cosmic system, enlightening a particular appearance. The central lump is believed to contain a high concentration of stars affected by the gravitational pull of the actual world. Considering that the world has an overflow of stars, it isn't surprising that a fraction of them bunch together to form this lump. Moreover, there are in excess of 400 globular clusters dispersed throughout the Andromeda system, which are spherical collections of stars bound together by gravity. In spite of being an enormous cosmic monster, the Andromeda cosmic system isn't alone in space. In fact, it has an escort of at least 14 known satellite worlds circling around it, forming an intriguing vast family. The interactions between the main universe and its satellites play a significant role in the evolution of their respective structures and development, adding to the rich variety of vast peculiarities in the Andromeda framework. The presence of a ring of dwarf galaxies surrounding Andromeda has been discovered. These dwarf galaxies are generally small and faint compared to Andromeda and the Milky Way. The discovery of this ring suggests gravitational interaction between Andromeda and the dwarf galaxies, demonstrating that the dwarf galaxies are under the gravitational influence of Andromeda, likely due to the massive gravitational pull of this world. The ring of dwarf worlds is a subject of dynamic research, as the specific nature of this association and the mechanisms that led to the formation of this ring are still under study and investigation by researchers to advance our understanding of galaxies, dark energy, and star development. Two powerful instruments are being utilized: the James Webb Space Telescope and the Dark Energy Spectroscopic Instrument, DESI. These instruments play a significant role in the study and examination of vast peculiarities, allowing the mysteries surrounding the Andromeda universe and its heavenly climate to be explored more meticulously and accurately. The James Webb Space Telescope is considered the most powerful telescope ever built and is designed primarily to observe the universe in the infrared range of the electromagnetic spectrum. This feature allows it to focus on the first galaxies forming in the early universe by detecting the faint light emitted by these distant galaxies. The James Webb Space Telescope will likely provide significant insights into the formation and evolution of galaxies, including the Andromeda cosmic system, and its observations will contribute to our understanding of the processes that have shaped the universe over time. On the other hand, the Dark Energy Spectroscopic Instrument, DESI, is specifically designed to study dark energy and galaxies. DESI utilizes optical spectroscopy, which consists of separating galaxy light into its various frequencies to analyze the spectra of millions of galaxies. Through this massive spectroscopic survey, cosmologists can measure the distances to galaxies and gather information about their properties, such as their chemical composition, development history, and motion. DESI's investigation of the distribution and motion of galaxies reveals insights into the confounding nature of dark energy, a mysterious force that drives the accelerating expansion of the universe. In the particular context of the Andromeda system, DESI observations have provided captivating insights into the transient history of stars within it. By examining the spectra of individual stars, DESI can uncover information about their chemical structure and origins. This allows astronomers to trace the history of star development and follow the evolution of stars within Andromeda. By learning more about heavenly motion patterns, researchers gain a better understanding of the formation and evolution of the universe, as well as its interactions with neighboring galaxies. Additionally, recent investigations have provided indisputable evidence for the presence of a heavenly halo in the Andromeda system that bears similarities to that of our own Milky Way galaxy. This discovery has illuminated the dynamic nature of galaxies and the complex interactions between them. Observations and simulations suggest that a significant number of stars found in the outer regions of Andromeda's heavenly halo have migrated from small satellite galaxies that were gravitationally captured by Andromeda over time. Several dwarf systems merged with the Andromeda system, taking their heavenly populations with them. This process of cosmic cannibalism is known as cosmic gradual accretion or merger. Cosmic mergers are believed to be common in the universe and shape the structures and characteristics of galaxies, including Andromeda. The presence of stars from different galaxies resulting from interactions and mergers with smaller companion galaxies helps scientists understand the kinematics and distribution of stars in the heavenly halos of galaxies like Andromeda and the Milky Way. By studying the populations of stars in these star halos, cosmologists can trace the history of cosmic mergers and interactions that have shaped these galaxies over billions of years. The heavenly halo contains stars that have been acquired by smaller satellite galaxies or star clusters, and their properties can provide valuable information about the history of galaxy mergers and assembly. This galaxy merger process has been a crucial factor in the evolution and development of galaxies like Andromeda and has contributed to the variety of features and structures observed in them. Through detailed observations and simulations, researchers can investigate the chemical structure, age, and motion of the stars that comprise the heavenly halos. This data allows them to reconstruct the timeline of cosmic mergers, identify the progenitor galaxies that contributed to heavenly populations, and understand the physical processes involved in such mergers. This approach is of utmost importance because should this immense universe ever come into contact with our own, it would be essential to be prepared with all available knowledge. The investigation of galaxies extends far beyond simply understanding their physical attributes and interactions. It delves into fundamental questions regarding the origins, structure, and destiny of the universe itself. One of the significant areas of interest is the role of galaxies in cosmic evolution. Galaxies are the building blocks of the universe, each serving as a lab for the study of star formation, black hole growth, and dark matter. Their formation and evolution can offer clues to the early states of the universe and the processes that have shaped its large-scale structure. Galaxies are not static entities. They are dynamic systems that evolve over time. This evolution is driven by various processes, including mergers, interactions with other galaxies, and internal dynamics. The study of cosmic mergers is particularly critical, as these events can trigger bursts of star formation, impact the growth of supermassive black holes, and reshape the structure of galaxies. The Milky Way itself has undergone several mergers throughout its history, and understanding these events helps researchers model its future interactions, including its impending collision with the Andromeda Galaxy. Recent research has also focused on the role of dark matter in cosmic evolution. Dark matter, an invisible form of matter that does not emit light or energy, is a critical component of the universe's mass. Its presence influences the structure and dynamics of galaxies, affecting their formation and evolution. Observations suggest that dark matter forms a halo around galaxies, influencing the rotational curves of galaxies and the distribution of visible matter. By studying the interaction between dark matter and visible matter in galaxies, scientists aim to better understand the nature of dark matter and its role in cosmic structure formation. Another key aspect of cosmic investigations is the assessment of cosmic feedback mechanisms. Feedback from star formation and supernova explosions can significantly influence the surrounding interstellar medium, affecting subsequent star formation and galaxy evolution. This process is essential for understanding how galaxies regulate their own growth and maintain their observed properties. High-resolution simulations and observations of nearby galaxies are helping to unravel the complexities of these feedback mechanisms, providing insights into how galaxies recycle gas and elements over time. The study of active galactic nuclei, AGN, is another exciting area of research. AGN are regions at the centers of certain galaxies where a supermassive black hole is actively accumulating material. The intense radiation and outflows from AGN can influence the surrounding galaxy, affecting star formation and the overall cosmic environment. By studying AGN, researchers gain insights into the growth of supermassive black holes and their impact on galaxy evolution. Observations of distant AGN provide a window into the conditions of the early universe, helping scientists understand the formation and development of galaxies in their infancy. The role of galaxies in the broader cosmic web is also a point of great interest. The universe is structured in a vast network of filaments and voids, with galaxies and galaxy clusters forming along these filaments. Understanding the distribution of galaxies within this cosmic web helps researchers study the large-scale structure of the universe and the influence of dark matter and dark energy on cosmic evolution. Large surveys such as the Sloan Digital Sky Survey, SDSS, and the upcoming Wide Field Infrared Survey Telescope, WFIRST, are designed to map the distribution of galaxies and investigate their role in the cosmic web in greater detail. Additionally, the study of galaxy clusters provides valuable information about the large-scale structure of the universe. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies. They are essential for understanding the distribution of dark matter and the effects of dark energy on cosmic evolution. Observations of galaxy clusters help scientists test the properties of dark matter, measure the rate of cosmic expansion, and study the growth of large-scale structures. Moreover, astronomical pursuits in cosmic investigations have significant implications for our understanding of fundamental physics. The study of extreme conditions, such as the interiors of galaxies and the regions around supermassive black holes, challenges the limits of our physical theories. Observations of these extreme environments can provide insights into the nature of fundamental forces and the behavior of matter under extreme conditions. The investigation of galaxies, therefore, intersects with high-energy physics, cosmology, and astronomy, contributing to a more comprehensive understanding of the universe. The advancement of observational technology plays a crucial role in expanding our knowledge of galaxies. Space telescopes such as the James Webb Space Telescope, JWST, offer exceptional views of the universe in various wavelengths, revealing insights about distant galaxies that were previously out of reach. Ground-based observatories equipped with advanced instruments such as the Very Large Telescope, VLT, and the Large Synoptic Survey Telescope, LSST, continue to provide valuable data on nearby and distant galaxies. The combination of these observational tools, along with theoretical models and simulations, enhances our ability to explore and understand the complex phenomena associated with galaxies. The exploration of galaxies is not only about observing their structures but also understanding their life cycles and interactions. The cosmic dance of merging galaxies can ignite new star formation, creating vibrant stellar nurseries. Research into the chemical enrichment of galaxies sheds light on how elements like carbon and oxygen are distributed throughout the universe, impacting the development of life-supporting environments. Furthermore, studying galaxy evolution informs our knowledge of cosmic timelines, helping astronomers piece together the universe's history. Each discovery fuels curiosity, urging scientists to refine their theories and seek answers to questions about dark matter, dark energy, and the ultimate fate of the cosmos. In summary, the investigation of galaxies encompasses a wide range of scientific inquiries, from their formation and evolution to their role in the cosmic web. By examining the physical properties, interactions, and feedback mechanisms of galaxies, scientists gain significant insights into the fundamental processes that shape the universe. The prevailing belief among most scientists is the Big Bang theory, which stands as the leading explanation for the origins of the universe. This theory encompasses the creation of stars, planets, and all life on those planets, including ourselves. Despite its somewhat whimsical name, the Big Bang offers a descriptive glimpse into what might have occurred initially. The universe was once condensed into a minute space smaller than a pinhead, with particles densely packed. From this minuscule point, a colossal explosion of matter and energy occurred, known as the Big Bang. This event, occurring billions of years ago, sets the stage for the unfolding of cosmic history. However, advancements in scientific data have led to increasing contradictions with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever constructed, scientists anticipated that its observations would bolster the Big Bang theory. Regrettably, after just 1 year in space, the telescope astounded scientists with its unprecedented ability to peer deep into the universe's past. The James Webb Telescope's remarkable capabilities have unveiled galaxies dating back to a time so ancient that it challenges our understanding of the universe's origins. This revelation has sparked a fervent exploration into what existed before the Big Bang. One pivotal moment in this quest occurred when astronomer Rohan Natu, working with data from the telescope, stumbled upon a galaxy dating back a mere 300 million years after the Big Bang, making it the oldest galaxy ever observed. Natu's discovery sent shockwaves through the scientific community, underscoring the transformative potential of the James Webb Telescope. Its mission to revolutionize our comprehension of the cosmos has just begun, promising to unveil unprecedented insights into the earliest epochs of the universe's existence. This epoch, scarcely explored before, holds the key to understanding the formation of the first stars and galaxies. The telescope's findings have defied initial expectations, revealing galaxies with characteristics surpassing previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, challenging researchers to reconcile these observations with existing theories. As scientists grapple with these discoveries, they confront profound questions about the fundamental nature of the universe and the forces shaping its evolution. Furthermore, the James Webb Telescope's technology is revolutionary. Stationed 1.5 million kilometers away from Earth, it is shielded from terrestrial interference and cooled close to absolute zero by its tennis court-sized sunshade. The telescope carries a giant segmented mirror and exquisitely sensitive instruments designed to uncover details of cosmic dawn never before observed. This epoch, known as cosmic dawn, occurred no more than a few hundred million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process of how this unfolded remains a subject of intense study, with theories ranging from the influences of dark matter and dark energy to the interactions among starlight, gas, and dust. The telescope's observations of galaxies from cosmic dawn offer a unique opportunity for cosmologists to test their understanding of these underlying phenomena. By scrutinizing these ancient galaxies, scientists can either confirm the validity of their current models or uncover gaps in understanding that could lead to profound new discoveries. Initially, it was projected that the telescope would find only a few faint and small galaxies in its pilot investigations. However, the reality has far exceeded these expectations. The telescope's very first images of the distant universe revealed numerous galaxies with ages, sizes, and luminosities that surpassed all predictions. This unexpected bounty of early galaxies has triggered a race among astronomers to claim new records for the earliest known galaxies. Each day brings forth claims of yet another record-breaking discovery, leaving the scientific community in awe and prompting a re-evaluation of our understanding of cosmic history. In the wake of the James Webb Telescope's findings, theorists and observers have scrambled to explain the existence of these unexpectedly mature early galaxies. Some speculate that flaws in the analysis of the telescope's initial observations may be responsible for these anomalous discoveries. However, the consensus remains that these findings represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The recent revelations from the James Webb Space Telescope regarding early galaxies raise profound questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists speculate whether these observations can be reconciled with existing theories, others suggest that they might be the first indications that the universe is even more intricate and peculiar than previously imagined. At stake is nothing less than our fundamental understanding of how the orderly universe we know emerged from primordial chaos. The early findings of JWST have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant epochs and faraway galaxies, but also on the very existence of our own Milky Way galaxy. As Mark McCarran, Senior Advisor for Science and Exploration at the European Space Agency, aptly puts it, "You build these machines not to confirm the paradigm but to break it. You just don't know how it will break." The origins of JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, G. Winger, then Deputy Director of STSCI, was tasked with envisioning what would come after Hubble. Despite initial reservations, Winger and a small team began laying the groundwork for what would eventually become the next-generation space telescope, later renamed JWST after a former NASA administrator. Unlike Hubble, which primarily observes visible light, JWST was designed to observe in the infrared spectrum, allowing it to peer much deeper into the universe. This capability is crucial for studying early galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its large and cold star-like mirror, JWST became the ideal tool for unlocking the mysteries of cosmic dawn. The need for JWST was underscored in 1995 when the Hubble Deep Field observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope capable of delving even deeper into cosmic history. After more than 2 decades of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of science observations. Early programs like the Cosmic Evolution Early Release Science Survey and the GRISM Lens Amplified Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded predictions. The JWST observations have challenged existing notions about the early universe, revealing galaxies that defy conventional models. These unexpected discoveries underscore the importance of pushing the boundaries of scientific exploration and highlight the transformative potential of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to unravel the mysteries of the cosmos, they are poised to rewrite our understanding of cosmic history and the forces that have shaped our universe into what we see today. The early observations made by the James Webb Space Telescope have astonished astronomers by revealing extremely distant galaxies. Almost immediately prior to JWST, the most distant known galaxy was GNZ11, discovered in 2015 with a redshift of 11, corresponding to a cosmic age of about 400 million years. However, from the outset of JWST observations, the GLASS team, led by Rohan Natu and another independent group, made a remarkable discovery. They identified a galaxy dubbed GLASS Z13 at a redshift of 13, approximately 70 million years earlier in cosmic history than GNZ11. The rapid pace of these discoveries was facilitated by simplified techniques for estimating redshift, which, while less precise than direct measurements, provide a quick assessment of a galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass comparable to billions of suns despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Dozens of galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited disk-like structures, a feature not expected to manifest so early in cosmic history. Furthermore, evidence emerged for galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard cosmological model, lambda cold dark matter, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, Galaxies of such size and luminosity should not have formed so early in cosmic history. The emergence of massive galaxies in the early universe presents a significant puzzle for cosmologists to comprehend. To understand this dilemma, it is essential to grasp the early stages of the universe's evolution. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of cosmic evolution, from chaotic beginnings to the structured cosmos we observe today, is thought to have taken approximately 1 billion years. JWST observations challenged this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing numerous small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has detected galaxies that are already sizable and luminous. Follow-up observations with instruments like the Atacama Large Millimeter Array in Chile have provided further evidence supporting the authenticity of these distant galaxies, ruling out the possibility of low-redshift interlopers. These groundbreaking discoveries open new avenues for understanding the early universe and may necessitate revisions to our current cosmological models. JWST continues to revolutionize our understanding of cosmic history, challenging our preconceptions and pushing the boundaries of astronomical exploration. The absence of detectable dust in the observations made by the Atacama Large Millimeter Array underscores the challenges faced by telescopes in confirming observations made by the advanced capabilities of the James Webb Space Telescope. As Rohan Nata noted, while JWST can follow up on its own observations, ALMA's difficulty in detecting the galaxy highlights the intricacies of confirming such discoveries. The implications of JWST observations are profound, potentially challenging the canonical lambda-CDM cosmological model and necessitating revisions. Michael B. and Cullen expressed astonishment at the results, suggesting a significant departure from our current understanding of cosmic brightness of these galaxies. He theorizes that early magnetic fields may have played a role in kickstarting star